So, today I will deviate slightly from there, because it is needed even to discuss properties of Gaussian states. So, what I will discuss today or maybe in the next class is some of the Gaussian operations, okay, which are very important in dealing with continuous variable system. And these Gaussian operations are such that after acting on Gaussian states it will produce Gaussian states. Okay. And these operations are also important to deal with optical gadgets. Okay. So, the first thing that I will describe is called quantum mechanical beam splitter. Right. So, beam splitter is like mirror. Okay. So, think of it like something like this. So, mirror, it has generally on the back side it is opaque, right. So, if light comes from here, so then you draw the perpendicular, if it is a plane mirror, then it will get reflected with the same angle. But for a beam splitter this is not fully opaque. So, some light can pass through. So, as a result what can happen is it will split this, let us say. So, this is not opaque, let us say there is some amount of light can pass through. So, then maybe something will go in this direction and something will get transmitted, okay. Because so the total intent. So, if I assume that this is a lossless beam splitter, so it is not absorbing any light, neither it is releasing any light. So, then this is a, so the energy, total input energy of light, which is intensity, should be same as the intensity of light here plus intensity of light here. So, intensity of light in the reflected beam plus intensity of light in the transmitted beam, that is the energy conservation, and this is true for classical light also, right, because this is a lossless beam splitter. So, fine. So, the total energy should be, so energy of this plus energy of this should be equal to energy of this input beam. When I deal with beam splitter, which is again lossless quantum mechanically, then things are slightly complicated. There, if I just say that this is one input beam and then I have reflected beam and transmitted beam, energy is conserved and this is a lossless beam splitter, but this is incomplete story. Quantum mechanically this is incomplete or inappropriate. Why? For quantum mechanical description of beam splitter, so this input beam corresponds to one mode, which may be described by frequency, polarization, so on and so forth. Similarly, this reflected beam and transmitted beam. So, when you deal with quantum mechanical beam splitter, one should have, apart from energy conservation, mode conservation, number of mode conservation. So, just one input mode cannot give rise to two output modes or vice versa. Two input modes cannot give rise to one output mode. So, you should have also the mode conservation. So, as a result you should have also a mode like this, input mode. Okay. So, two input modes and two output modes. Okay. So, that means that you will have energy conservation and mode, number of mode conservation. So, these are essential for lossless quantum mechanical beam splitter.
But what is the problem? So, if I let us say higher photon of frequency omega, let us say, and Then it gets split by omega by 2 and omega by 2. What is the problem?
Energy is conserved, yes, no problem in that. But the mode conservation is because we are dealing with non-relativistic quantum mechanics. So there we don't assume any.
Oh, new number of particles. Okay, I see. Yeah,
Okay.
I can see.
In field theory, of course, you can have this.
I understand. Good.
Right. So even if there is no light, even if it is a vacuum, still this is needed. Right. Okay. So now you can think of it like a dynamical process. So you have input light, input state together, and you have output state together. So this transformation should correspond to a Schrodinger evolution, and therefore this gadget should correspond to a unitary transformation. Okay. So therefore quantum mechanical, I mean one can of course describe lossy beam splitter, but that will be more complicated. I'll talk about it later. Quantum mechanical lossless beam splitter. So this corresponds to basically a unitary transformation. Now unitary transformation of what? Unitary transformation can be, so basically this is in the physical space. So you can think of it like in the configurations, in the phase space. So phase space of this input beam and this input beam. That means the phase space should be, this is, so here it is, maybe this is for, let us say Q1 P1 and this is say Q2 P2. So this is a 4-dimensional phase space, right, for input. So output should be also 4-dimensional, and so what you can think of is,
Vacuum mode does not have any photon as such.
that's okay, but
How can I specify the state space? Q to P2?
phase space should be there, right? Yeah, because even if it is vacuum, still it corresponds to a Hilbert space, right? See, vacuum is a special case. You can
But that
have,
is your mathematical machinery, right?
no,
Is
no,
it
no, no.
physical?
See, even if it is not a, see, vacuum is a special case. It can be anything.
Okay.
So if you have a single mode, that should correspond to a Hilbert space, right? So single mode system in our language, it should correspond to a Fock space. Okay. So in this case, this is a Fock space. So this is one mode. I am not considering more than one mode.
But what is physically there? Like, let's say I am an experimentalist. What is there?
Yes. So for experimentalist, if you just send this kind of light, it will not work. So you will have to have a mode selector. So if you send laser light,
Okay.
it will select a particular mode. I mean, which mode you will select, that's up to you.
Okay.
But it will have to be, so one particular mode has to be selected, and that mode is specified by the frequency, polarization, and all other things. So even if there is no photon, still that mode will be fixed.
But assuming that there is like a plate, I mean, let's think that there is a plate close to the beam splitter, okay?
Yes.
So then, because there is a plate, there should be some kind of a Kashmir fluctuations of the vacuum itself. So, I mean, by changing the plate, the separation between these plates, maybe we can differentiate between different vacuum states coming in, and then whatever we are seeing at the output, there might be some differences. Does
Yes.
it mean that way?
No. His point is, I mean, if there is no physical particle here, I mean, how will I figure out? Because this vacuum
Just a
can be.
vacuum state, that's mathematically.
So the vacuum is here, it corresponds. See, this vacuum is a special case. This can be any state, not necessarily vacuum.
Right.
So this one, that you will have to select a particular mode. How will you select a particular mode? There are different ways of doing that. Okay. So for example, if I send a laser light, it will have different modes, but I can in principle choose a single mode there. Now, if there is in principle no photon, still it is a mode. Okay.
You just think of it as a limiting case of one light that you are shining in, and then decreasing the intensity of
I understand. I mean, very low intensity light, for example. So the point is that I mean, you will have to take a particular mode. What mode you choose, that is up to you. I mean, that depends upon what laser light you are using. But point is that, as I said, this, see, as a whole vacuum, it doesn't mean any particular mode, right? But whenever a creation operator of a particular mode acts on vacuum, it will create a photon of that mode.
Right.
Okay, so it doesn't matter what vacuum you choose here. But for our purpose, because it's a generic treatment, you'll have to choose a particular mode. So I am not using this only as vacuum. You can choose any state. Vacuum is a special case there, but you'll have to choose a mode here, another mode here.
And in principle, two laser, are you saying? Like I want to understand.
Yeah. You send a laser, but in principle, what you can do, you can see laser will have more than one mode generally, but you can select a particular mode, and then so there are mode sorter basically.
I see.
So then you send laser light through that mode sorter, and then one particular mode light will come, one particular mode light will come.
Okay, but the mode is still there, even the photon is not present.
Yeah.
I see.
See, I cannot deny existence of vacuum because we know that there are effects which happen due to vacuum.
That is.
Also, these two states are kind of necessary so we can write a unitary, right? Because without it, we can't really write a square matrix.
Repeat it again.
So we have like two of these inputs.
Yes.
And unless we have two, and there are two outputs, so we have, for instance, something like a 2 + 2 unity.
Yes, that is true.
If we had only one, then we could not write that.
Yeah, then it will not be unitary.
Not
Yes,
right.
yes, that's true.
Yeah.
That is true.
Since you are already constraining the number of modes conservation.
Yes.
That part is good.
So basically, the input Hilbert space, which is tensor product of Fock space here, single mode Fock spaces. Output Hilbert space will also be tensor product of single mode Fock space, single mode Fock space.
Must be of the same dimension.
Yes. Yeah. Otherwise, it is not unitary.
Yeah.
Okay. So therefore, what I can think of is, to make our life easier. So this is in the physical space, whatever happening, particularly in the phase space. Okay, what is happening in the real world. So then this transformation corresponds to a unitary matrix, 2 by 2 unitary matrix. I mean, you can say spatial, what is that called? Anyway, unitary matrix. So U, which I will write here as e to the power, let us say, I epsilon cosine theta, e to the power I phi sin theta, minus e to the power minus I phi sin theta, e to the power minus I epsilon cosine theta. So this is the most general special unitary matrix, right? Determinant one.
This acts on A and A daggers, right?
Yes. It will act on, it will act on this. So this corresponds to, let us say, A1, or let us say this is A and A dagger, and this corresponds to B and B dagger. Okay. So this is the unitary transformation. So if I look at the outputs, let us say this is A prime and B prime. Okay, so you can call, let us say, this is A prime dagger, this is B prime dagger. Then this will be this unitary acting on A and B. I mean, unfortunately, I could have used these hats, but these are not Hermitian. So you will have to understand it from the context. Okay. Is that clear? So therefore, this is a unitary transformation which acts on the physical space. I mean, acting like this is equivalent to, if I call it like P1 prime, P1 prime, Q2 prime, P2 prime, then this means that you act on Q1 hat, P1 hat, Q2 hat, and these are all prime. P2 hat. So, this will be a corresponding, this is a 4 by 4 matrix, okay, 4 by 4 real matrix, and acting on Q1, P1, Q2, P2, right. So, this is a canonical transformation. So, you can verify that this is, so you understand that these are same, right, in the sense that yes. So, you can write your Q1 as a plus a dagger by root 2, P1 as iota a dagger minus a by root 2, Q2 is equal to b plus b dagger by root 2, and P2 is equal to iota b dagger minus b by root 2. So, this is equivalent transformation, only thing is this is a 4 by 4 real matrix, and you can verify that this is a canonical transformation in the sense that all these properties will be satisfied. So, if I call it as a typical entry of these as let us say R j hat. So, R j hat R k hat will be same as R j prime hat R k prime hat. Okay. So, this will be the canonical transformation. Yes, yes. So, this is a symplectic element, symplectic matrix, yes. SP4R, yes. Okay, good. So, is this clear? Right. This is commutation, This is the canonical commutation relation between the input and the output quadrature. These are called quadratures. Okay. Sorry?
So, can you explain about that RJ and RK again?
RJ is you call like R1 as Q1, R2 as P1, R3 as Q2, R4 as P2, and similarly here on the left hand side you call Q1 prime hat as R1 hat, R1 prime hat. So, this is your R1 prime hat, P1 prime hat is R2 prime hat, Q2 prime hat is R3 prime hat, and P2 prime hat is R4 prime hat. Okay. So, this one is, so Q1 hat is equal to R1 prime, P1 hat is equal to R2 prime, R2 not prime, and Q2 hat is equal to R3 hat, and P2 hat is equal to R4 hat. Okay. So, this satisfies the commutation relation. For example, commutator of R1 and R2, which is commutator of Q1 and P1, and which I know is iota, h cut I am taking to be 1. Okay. So, this is iota. So, same will be the case with R1 prime hat and R2 prime hat. This is also iota.
So, that you have also written the commutation.
Yes, yes. No, this is a commutation relation. Sorry, yeah, this is the commutation relation. Okay. Is that clear now? Okay, good. So, on the physical space, that means in the phase space, this is your transformation, which is a canonical transformation, which corresponds to this unitary in field. Okay. Right. Okay. So, now the question is that this I understand, this is a canonical transformation on my physical space. Equivalently, this is on the field operators, this unitary. But how to get the action of beam splitter when I know the joint input state? So, what will be the relation between the joint input state and joint output state? Okay. So, if I call it as capital psi in and call it as capital psi out, then how are they related? So, I said that this has to be related by Schrodinger evolution through unitary, but this is an element in the Fock space, right. like HA tensor product HB, which is infinite dimensional, and this is also an element in HA prime tensor product HB prime, which is essentially same as this. So, this is infinite dimensional state, this is also infinite dimensional state. So, they should be connected by unitary because this is Schrodinger evolution, but that unitary cannot be this unitary because this is a 2 by 2 unitary. Okay. So, how will I get that? So, basically the question is what will be the unitary representation of this canonical transformation in the Fock space? Huh? Outer product?
Psi n and psi r. Get psi n.
Yeah, that is true, but I need this for generic case. So, this has to be a linear transformation, it cannot be dependent on my input and output. Okay.
Sir, how many free parameters are there? Because I think we can reduce the number of free parameters from this number of 4 parameters, because we can do a canonical transformation between the second mode, which is vacuum.
Actually, there are 3 parameters, right? Epsilon, phi and theta.
Yes. So what I'm saying is that for the vacuum state that we are putting in, so let's assume that the vacuum phase space elements are like Q2 and P2. Okay. So any canonical transformation between Q2 and P2 is automatically allowed, because I mean that does not change the vacuum. So we can reduce like one parameter or have a gate choice to basically reduce the number of parameters as much as possible. So
That is true, but we have a much simpler option for this. So,
Some over outer products.
yeah, that is also true, but we have a much simpler option for that. Okay. So, this is like this is a, you understand that this is a continuous transformation, right, because these parameters are continuously, I can vary them, and this is a symmetry preserving transformation, that also we agree, right, because it is a canonical transformation, it is a symmetry preserving transformation, is not it? I mean, if I take angle between two vectors, it will remain same. Okay. So, every continuous symmetry preserving transformation on physical space should have its representative in the Hilbert space, I mean acting on the Hilbert space, and that representative has to be a unitary representation. This is what this Wigner's unitary anti-unitary theorem tells us, right. So, therefore, we need to figure out what will be a corresponding unitary representation of this, and that representation should be faithful. Where is unitary representation?
So you have just write in terms.
Yes,
of
this
zero
is
by
unitary,
Uh,
but this unitary is just 2 by 2. I need unitary acting on the infinite dimensional Hilbert space. That is why I am saying I need a representation.
Okay.
Okay?
Okay. I see.
Is this clear?
You need a representation of an unitary operator for corresponding to this canonical transform.
Unitary operator or this canonical transformation, these are equivalent. Okay? This is 4 by 4 canonical matrix, canonical transformation, I need a unitary representation of that. Okay? Right. Okay. So, let me write down. So, instead of u, what I will do is, to make my life easier, I will call it at B. Okay.
you can write A dagger and B dagger as like a Q, like in terms of Q and P's, right?
Yes.
So you have the transformation for A dagger and B, A prime and B prime. So you will also have the transformation for A dagger and B daggers. So from that you can work your way backwards for the transformation between Q prime and.
That is what, that is what I have written.
So that's the 4 plus 4.
That is the 4 plus 4. Yes. This is equivalent.
Sir, A and A dagger, B and B dagger, so they are infinite dimensional operators, right?
Yes. Yes.
So then how do you define this operator U there?
This is just a linear transformation. So, like what will be A
Ultimately, you are
prime?
putting them in a
Yeah, so what will be your A prime? A prime will be like A e to the power I epsilon cosine theta plus B e to the power I phi sine theta. Right?
oh, in that sense.
Yes.
Okay,
It is in the Fock space.
it is in the Fock space.
Okay. So, as I said, I mean, for my purpose, I will replace it by B because this is beam splitter matrix. Okay. For unitary matrix I will use U. So, this B which is function of theta, phi and epsilon, this is once again I will write it e to the power I. By the way, can you see whatever I am writing on the right hand side of the board? Hello?
Yes, sir. Able to see.
Okay, okay, okay. So, this is cosine theta e to the power I phi sin theta minus e to the power minus I phi sin theta e to the power minus I epsilon cosine theta, right. So, now to get this unitary representation I will have to do a trick to make my life easier. So, what I will do is let me write it as e to the power I epsilon prime 0 0 e to the power minus I epsilon prime cosine theta sin theta minus sin theta cosine theta and then e to the power I phi prime 0 0 e to the power minus I phi prime. So, let me write it like this. So, what is it that I need to figure out? What are these phases epsilon prime and phi prime, and this is just simple product. So, product of these three matrices. So, this is what is known in the literature as, I may be wrong in the spelling, Iwasawa decomposition. So, this spelling may be wrong. Okay.
Just Euler angle, like basically decomposition between three Euler angles, right?
Yes. So, basically yes, exactly. So, basically the first and the last corresponds to rotation about z axis and this corresponds to rotation about y axis, for example. Okay. So, this is what we will have to see, these Euler angles are I mean one should be careful. You first rotate about body fixed space fixed z axis, then body fixed y axis or x axis, then body fixed z axis, something like that. Okay. Yeah. So, anyway we will come back to this. This is just simple product. Okay. That is what. So, I will have to see that. Okay. Whether I can do that. Yes.
So why cos theta is not having prime, theta is not having prime?
I can do that also, but to make our life easier, if I get a solution of this, then that will be enough, right? Yes. So, now tell me what is this. So, first two, what will be that?
E to the power I epsilon prime cos theta. Then that would be sin theta minus sin theta cos theta. Right.
Do you agree with me? This is what you will get. Now, can I compare with this? Okay. So, what will be the solution? So, epsilon prime plus phi prime should be equal to epsilon and epsilon prime minus phi prime is equal to phi. Is that okay? I think that is fine, right? Okay. So, this means what? epsilon is equal to, or sorry, epsilon prime is equal to epsilon plus phi by 2 and phi prime is equal to epsilon minus phi by 2, right. So, therefore, I can replace it by epsilon plus phi by 2, epsilon plus phi by 2, this is epsilon minus phi by 2, epsilon minus phi by 2. Is that okay? So, I have a solution, right. So, now if I look at these 2 by 2 matrix, so look at this I can write as so exponential of iota epsilon plus phi times half sigma z. This sigma z is Pauli 2 by 2 matrix. So, look, this and this are same. Can I do that? Can I claim that? Because sigma z has eigenvalues plus 1 and minus 1. So, the plus 1 eigenvalue corresponds to this diagonal matrix, diagonal entry, and this corresponds to the minus 1. Okay? Multiplied by, what about this?
Sigma x plus I sigma.
X plus sigma by some form.
Sigma x plus I sigma y.
Be careful.
Sorry, yes.
Sigma n dot sigma n.
Kind of.
Yeah, after you will write
Sigma y.
what sigma y.
Sigma
only.
y.
So, then what will happen? This is your angle. So, this is basically iota theta sigma y, see exponential. If you expand it, it will be cosine theta
Ah, okay. Identity minus
identity and then plus
plus.
iota sine theta sigma y. And iota sigma y is this matrix 0, 1, minus 1, 0.
I see.
Okay?
No, this was string. It is not so easy to tell. Okay, I see.
Is it okay?
Ah,
And this I have written because to make it like this. And then multiplied by exponential of again iota epsilon minus phi half sigma z, right. Is this clear? Okay, good. So, up to this everything is fine. These are Pauli 2 by 2 matrices, things will be easy for this. So, let me erase this part again.
So this is just like you are writing a general unitary in terms of x and
2
z.
by 2
Yeah,
unitary, special unitary in terms of product of these exponential of Pauli matrices.
Right, right.
Now, what is the advantage of writing in this way? You see, half sigma x, half sigma y, half sigma z, they satisfy the angular momentum algebra, right, SU2 algebra. Okay. Now, when you talk about algebra, I do not talk about what dimension I should consider. So, now I will go from 2 dimension to infinite dimension, because I am dealing with representation in algebra. As I said, I do not care what dimension you have, so far as it is faithful. Okay.
But in all dimension, how can you guarantee this decomposition is possible?
I do not care, I do not have to, I only look at the representation of this half sigma y, half sigma z in the corresponding infinite dimensional system. Okay.
So representation by definition concerns the good algebra.
Right. No, but I am saying that I can write a general unitary, let's say, I can write
See,
it
when
in
I write in
relation
terms of, so this will do, okay, let me erase this part. So, this I can write as therefore exponential of iota epsilon plus phi, this is my jz, this is the angular momentum jz operator,
Right.
okay, then exponential of iota 2 theta jy, and then exponential of iota epsilon minus phi jz, right, where they satisfy jj jk is equal to iota epsilon jkl jl, right. This is the Levi-Civita symbol.
Right.
So, this I can always do.
Maybe we'll proceed. I'll understand it.
Yeah. So, now, so far, I mean, I have not told anything about the dimension. Only thing is this is in 2 dimension, fine, but I'll have to lift it to infinite dimension, because I want to get a representation in infinite dimension. Okay.
My problem is like in infinite dimension, how do you know that this kind of decomposition is possible?
That's okay, that is fine. I don't have to, but faithful representation means what? It should satisfy these, what is that called? Homomorphism. Okay. So, this is a homomorphism, the product of 2 group elements in the representation space also satisfy the same order, same type of product. Okay. I mean, if I take 2 group elements like here, if I take G1 and G2 and take their product, okay, so then the corresponding unitary representation, let me call it as UG1 and UG2. Okay. So, this U of G1 G2, it should be equal to this, right. So, what I am talking about, a unitary representation of this unitary matrix. Okay. So, unitary representation of that unitary matrix should be equal to unitary representation of this one times unitary representation of this one times unitary representation of this one in the infinite dimension, is not it?
So that means even when I am lifting the okay, you are lifting the dimension, but still the group homomorphism structure still.
Yeah, the representation theory means that. Okay.
That is. Okay, I'll cover that.
Yeah, maybe perhaps one should look at this. Anyway, this is you can look at any book on representation theory; it will be there. Okay, good. So now, so here is our starting point to go to infinite dimension. Now, you should remember that our input Hilbert space is tensor product of 2 Fock spaces, output is also tensor product of 2 Fock spaces. So, this operator, when I lift them into infinite dimension, they should be Hermitian operators acting on tensor product of 2 Fock spaces, right, Jz, Jy, etc. So, how to do that? So, fortunately, we have a way out for that, and which is given by of the SU2 algebra. When I talk about algebra, I only talk about the generators. Okay. So, Swinger has given this double oscillator representation of SU2 algebra, and this SU2 algebra, the generators are these J, Z, Jy, Jx. Okay.
Can I just repeat? Sorry, I missed this part. What do you want to do now?
So, now I want a representation of Jz, Jy, and Jx in double Fock space, okay, tensor product of Fock spaces. And these are the generators. So, I will have to consider representing them in terms of the oscillators A and B operators. Okay, A, B, A dagger, B dagger, whatever you want to call. Okay, right? And Schwinger has already given that, and this is a faithful representation of SE2. Any dimensional representation can be obtained from here. Once you fix the total photon number. So, what will be the representation for Jx here? So, I am not writing Jx equal to, but this means its representation. Okay. So, this is A dagger comma B dagger. This is a row vector, then half sigma x, then AB. Now, can you tell me what will be this? Sigma x is 0, 1, 1, 0. Okay, so this is A dagger, B dagger, then half 0, 1, 1, 0, and then AB. What is this?
That must from something of A dagger and B dagger.
A dagger B plus
This is
so that AB will be upside down.
B dagger,
A dagger B plus B dagger.
A dagger B plus B dagger.
B dagger B plus, right?
Plus
Plus B dagger A.
B dagger.
Well, B and A they commute because they are two different. So, plus A B dagger, right? Is this clear? Similarly, JY, A dagger B dagger, half sigma y AB. So, which is A dagger B dagger, then half 0 minus iota iota 0 AB. What will be that?
I by
That will
2
be
A dagger
minus
B
sign.
minus A dagger.
I by 2,
A dagger B minus A dagger.
A dagger B minus AB dagger, right?
The opposite. Or maybe the opposite.
You'll have to be careful.
Yeah, it should be minus I by 2.
Yes, minus A dagger B plus A B dagger. Minus A dagger
Just
B.
put a minus I there.
Ah,
Okay. That's what.
right.
Right?
That is also.
Okay. And then JZ corresponds to A dagger B dagger half sigma Z AB, which is A dagger B dagger, then half 1 0 0 minus 1, and then AB. And this is
Half of A dagger A plus B dagger. The number of
half A dagger A, right?
A dagger A minus
A dagger A minus B dagger B, right?
This is just like angular momentum algebra, right?
Yes, yes, yes. They satisfy the angular momentum, that algebra, angular momentum algebra. Okay, right? So here you see that, so in this case there is a conserved quantity which is basically half A dagger A plus B dagger B. Why it is a conserved quantity? Because it corresponds to the unitary transformation of beam splitter. This is the total energy, well, half of the total energy. Okay, so this is a conserved quantity, but these are not. So that is a basically an invariant. Okay, total I mean half of the total photon number.
Oh, JZ is also not invariant.
No, no,
JZ
no.
is also not conserved. No?
No, JZ is also not invariant.
Oh.
invariant means if you apply U that quantity U dagger, it should be that
It should
quantity.
remain same as this. That corresponds to the energy conservation. Right? Okay. Right. So for our purpose, so therefore, if I look at this, let us come back again to the beam splitter matrix. What notation is this? Epsilon phi this. These are two phases, and this is the angle. So this I'll just correspond to it. I cannot write equal to. This correspond to it like exponential of iota. What is the first one?
Epsilon plus phi.
Epsilon plus phi. Now this is J
Half of A dagger.
Z. Huh?
Okay.
So Jz is, what is Jz? Half of A dagger A minus B dagger B. exponential of iota, then twice theta, right?
Right.
And then this is
I by 2.
I by 2
A B dagger minus A dagger.
a b dagger minus a dagger b, and then exponential of iota epsilon minus phi.
Are you sure this I will drop off? Oh, okay. I by 2.
Yeah, it will. This is I by 2, right?
I by 2.
And this is half again a dagger a minus b dagger b, right?
Right.
Okay. Right. So what is this? I mean, this is, if I act, for example, this operator, exponential of I, it's a sum angle eta, and then a dagger a minus b dagger b. This is acting on both the modes. So let's say this is acting on n and m. This is on a and b, let's say. Okay. So what will happen, because these are commuting, so I can write it as exponential of iota eta a dagger a acting on n tensor product, exponential of minus iota eta b dagger b acting on m.
Right.
So this will be exponential of iota eta, and then this is n, because this is number times n, and then from here it will be, so I will basically have n minus m, again n m, this nm means this tensor product. Okay. Is that clear? So basically it introduces a phase, global phase, this transformation. So this is not very important, this part as well as this part. But you can of course take them into account, but the actual beam splitter, what is the trick in beam splitter, is for this part.
Right.
Okay, which is the non-trivial part. So unless otherwise stated, by beam splitter transformation, I will only consider this part.
So this Schwinger's double oscillator representation, can I lift it to the, if I have 3 oscillators or something like that?
Yes, you can, but that will not be faithful. So SU3 has also a triple oscillator representation,
Okay.
but that will not be faithful.
Okay.
In fact, our colleague Ramesh Anishetty and one of his PhD students did that. Huh.
So that B operator changing this A dagger, B dagger. Here your B that actually that exponential operator changes the state, right? Input state to output state.
Yes,
Okay.
yes. In fact,
And
yeah, tell me, yes.
okay, so can I talk about eigenvalues of, let's say, this 2 cross 2 JX matrix and the eigenvalue of this half of A dagger B plus A B dagger?
Yes.
So then how do we like correspond the eigenvalues, or
Why
how
do you
to
want to correspond the eigenvalues?
No, because you are saying that the representation of JX is this one, right?
Yes.
So I mean, I want to just realize that how.
So when we talk about representation, in group theory, here it is unitary representation, we only talk about in terms of the group action. Okay.
Okay.
So how two group elements will act on each other,
Mhm.
the representation, unitary representation should reflect that part. I don't care whether the group elements are matrices, what are their eigenvalues, etc. I don't need that. Of course, the eigenvalues of this 2 by 2 matrix and eigenvalues of these infinite dimensional matrices are different.
That's true. Okay. So let's say that in 2 cross 2 Hilbert space, so you define a unitary which preserves the norm.
Yes.
So if you go to the infinite dimensional Hilbert space, or the representation of that 2 cross 2 infinite dimensional Hilbert space, so there if you get a unitary which preserves the same kind of norm.
Norm has to be preserved because this is a unitary representation.
Okay. Then how do you know that exactly this will be the representation?
See, this is one of the representations. Nobody tells you
Okay.
that there is only unique representation. This is one of the representations,
Okay.
and this is enough for me. You know, see, this is how physics is so beautiful when you deal with symmetries.
Okay.
Okay, so you don't have to care. Once you go, see, this is needed because we have to deal with Hilbert spaces. Okay, states and operators in Hilbert space. This we will have to do. Even if it is not there, but still, study of symmetry tells you what are the things that you should look for and what are the things you can forget about.
Okay.
So here is A dagger A plus B dagger B the only conserved quantity. You think if I compute J square, will that also be conserved?
J square?
Yeah, J square. Like that's an operator there.
J square will be of course conserved. Yes,
Both of them are.
yes, yes, of course. This is immediate conserved quantity, you know, because this is energy conservation. This means energy conservation. J square, if you consider, of course, that is a conserved quantity. Yes, yes, yes. Okay. Is it clear? So therefore, from now onwards, unless otherwise stated, by being splitter transformation, I will only consider this. Now, yes, any question?
I was just thinking, like, we have ignored the phase terms, but if we had some kind of phase.
Of course, it will come, but no, now I am only considering beam splitter action, but if you want to consider phases, of course, you will have to take that. Yes. Particularly this one. Yeah, this one you will have to consider first.
Yeah, because the other one I think is a universal.
You can forget about that.
So
Yes.
I think that one is first one is inverse. Second one is
Yes, second one is relative, so it will be different for
different modes, number states.
But anyway, I mean, if it is needed, I will consider that.
So we are just basically setting only theta as non-zero.
Theta is not.
Others we are setting as zero.
Yes, epsilon and phi we are setting 0. Okay, good. So now let us look at these transforms. So therefore, from now onwards, I will consider this as my beam splitter transformation. So this is, I mean, this corresponds to. So this as a matrix, you understand, right? This is a 2 by 2 matrix. What is that? Sine theta minus sine theta cosine theta, right? I think this was the matrix, right? Because it over I theta and I epsilon and I phi, they are 0. So this corresponds to exponential of now it is minus, so this is theta A dagger B minus A B dagger. Is that a correct statement? Yes. Okay. So this is, and this is of course unitary, right? So this acts on this infinite dimensional Hilbert space H A tensor product H B. This acts on that. So next question is, what will be the action of this thing on N and M? So this is on A B. Okay. What will be the action? And this is, you can see, it is non-trivial, because here you cannot use, split this using Baker-Campbell-Hausdorff formula, okay, because this, you can try that, but it will not work. Okay, so take this thing, theta A dagger B,
They are not non-commuting. That's why I think you can.
non-commuting, fine, that is okay. No, you take this one, A B dagger, right? So let us take this thing. So what will be this? This is minus theta square A dagger B A B dagger and minus theta square A dagger A B dagger B, right? So now this is A will minus theta square, this is A dagger A, and this one Now, what is this?
B dagger B. That come as the total as the B dagger.
Theta square b dagger b, right? Okay. So, this is what? Minus theta square twice theta square. I think this is j z, right?
Right. This is identity, not Z.
Not identity.
No, not identity.
Look at that j z. This is half a dagger a minus b dagger b, right?
It's infinite dimensions. How can only these two operators? But minus sign is not there.
Yeah, I think that there should be a relative plus sign
Okay,
between
okay.
the two.
Yeah.
Where is relative plus sign?
Like it's
No, no.
minus
It's
theta
right
plus
in
theta.
some sense because here must be A dagger A minus B dagger B, right? If you want JZ,
Yeah.
it must not be identity. That is a different thing.
Yeah, that is fine. This is plus theta square.
Okay, yes. There are two.
No, but you have taken minus. Okay, minus minus two is theta outside. square. Sorry.
Yeah. So, now let us take this thing.
Why don't we just brute force expand it out in power series and just
Yeah, that of course true. That is of course true. Yes, but now what is it? The next thing what we need to do is I'll have to take.
Know that why because first drop does not.
Yeah. So let us take this. What was the thing? A should commute with commutator of A and B, and B should also commute with commutator of A and B, right? So, theta A dagger B and then commutator minus twice theta square j z. It will not commute. Okay. So, therefore, you cannot use Baker Campbell full stop. Okay.
Taylor series expansion is on.
Kind of. Okay. Yes. But you know, we are not so dumb to use Taylor series expansion. We will have to use something else. Okay. So, we will come back to this later. Well, no, I will have to do it now only, you know, then I cannot come back later.
That's what you
Okay. Yeah, but why do you do for small theta when I know what to do for generic theta?
Okay, let's see what you want. What you are limiting theta. Limiting. We want to see what we here.
Right? Okay. So this I can write okay. Now you should explain whether this is correct or not.
It is becoming more difficult than the previous.
No, I think it has now got some beautiful expression, I guess, right? Baker house dot kind of thing.
But let's see.
Baker
This is unitary, right?
This is unit.
Okay. So, you apply this here, this is this times this. So, in between you introduce identity, which is this times this one. Okay. I mean this part times is dagger.
But you have A and D.
Wait. Okay. So, now
Definitely do it.
yes, you do it repeatedly. Okay.
Okay.
So, like u A dagger to the power n u dagger.
Okay.
So, you can write it as u A dagger u dagger to the power n, right?
That is okay.
Then yes, how did we get the last term?
No. This is, of course, you will have to have, yeah. So here it was U, right, because this was not there. This is identity,
Oh, there has to be a U inverse in the last.
not U inverse. It should be U here, something like that. Okay. This I can always do.
Right.
So this is fine.
Yes, that's what I have done.
And then we have to know the action of U on vacuum.
Where is vacuum? Oh, that will no. This vacuum is this one. I have not done anything here. This is the vacuum.
No. Just wait a minute.
So this is exponential times A dagger to the end times exponential.
Exactly.
And that one is exponential. And these
B dagger to the power m.
exponential next to each other cancel.
Oh, okay. Sorry.
And there's
Sorry. There is something missing here. Sorry. Yes, you are correct. Yes. So it should be, this is minus. So this should be plus.
But this what? But it will not have any action on its identity action on the.
Let us come to that later. But is this the correct one?
Yes.
So after this, you will have this term. Sorry. Yeah. Thank you. Okay.
Still not following.
Still you are not following?
No, I'm not following.
Okay. Let me make my life easier. So call it as U. Okay. This is U. So what is it? This is U, A dagger to the power n, B dagger to the power m. I mean, forget about this part. Okay, this part and this one. This is okay.
Okay.
So this is unitary. So what I will write, A dagger to the power n, U, B dagger to the power m.
Right. Still following.
So then we can write it U, A dagger,
U
U to the power n.
Right.
Sorry, A dagger of this to the power n.
Uh-huh.
So is that a correct statement for this?
This is correct statement.
Right?
Still now.
Okay. Now for this part, I'll write U, B dagger to the power n, U dagger U.
Okay, fine.
So this is U, A dagger to the power n, U, B dagger, U dagger to the power m, then U.
Oh, okay.
And that's what I have done.
Now it is. Yeah.
Right.
Okay. So now if I look at this part, there is only one term which will survive if I expand it. So which is basically 0 0. So this part is basically this first term, identity. Right? Yes. Will vanish. Yes.
জায়গার কোনো না কোনো কম্বিনেশন থাকবে যেটার একটা অ্যানিহিলেশন অপারেটর
Exactly.
Okay.
destroy করে।
Okay.
Okay. So that is why I have step jumped. I said this should be
I see.
0 0. Okay. So you can forget about this term.
Okay.
But then still we have this.
Yeah, still we have mess.
Still we have mess. Still we have mess. Yes, exactly. We have mess.
How this A and B evolve under A dagger?
Correct.
No, but that will be then I can use Baker Campbell.
Not Baker Campbell. Well, I don't know what is it called. So up to this, is it clear? Yeah. Yes.
Sahil is commenting that if Mace is on the board, you are the Mace manager. That is Sahil is commenting. Okay, fine.
What does it mean?
Mace is on the board, you are the Mace manager.
You're managing the mess.
You are manager.
Sorry.
That's what's happening. That you have this A B dagger and
That's
A dagger
okay.
B dagger.
Right.
So
Right.
what you have in something in the Fox space.
Yes.
So what it means is that you can take one like step up, and that has to come at the cost of the other one.
Yes.
So when you have this one, so the final sum will be somewhere n minus k m plus k, etc. And this k.
So
should
this
run
basically
over different-
distributes the number of particles
Exactly.
among
So,
the two outputs.
I mean, if there
So
is
this
like-
is just statistical distribution according to the the probabilities of transmission and reflection.
yes.
That's what
This
it does.
should be like sum over k n minus k m plus k.
Exactly.
And these coefficients are given by these
Exactly.
Nebocine
Yeah, that you can do, but let us do it a little bit more here, and then we can figure out.
Your goal is now to get a expression of the state in terms of all the excited states with kind of thing.
Yes. So basically, this beam splitter action, we will see that it will. So we have input n photon and m photons. Total number n plus m. So this beam splitter, lossless beam splitter, what it does, it distributes this total n plus m photon along two output directions. Okay. And the distribution probability will be according to some binomial distribution, which depends upon the reflectivity and transmittivity coefficients of the beam splitter.
But I missed Shilpa's argument. What he was saying?
No, I mean, the argument is simply that the photon cannot go anywhere, right? The total number of photons is constant. And if you have n photons here, the total number of photons is fixed. Now, all the beam splitter does is that you
distributing.
total number of photons
Yes.
and then distribute. And the distribution coefficients are just fine.
True.
Exactly.
I mean, you can do that, but this is what you do.
Yes.
That means we will get Bose-Einstein.
No, it will not, it will not incorporate anything quantum in it if there is nothing quantum in the, to begin with, that is in the input. Neither can it destroy anything quantum in it.
Okay, fine.
Okay, good. So let us now look at this part. This part, n will come anyway automatically. So theta A dagger B minus, what is this? A dagger, right? Minus theta A dagger B minus A B dagger. So here we use this formula of Taylor series kind of expansion, A dagger plus 1 by factorial 1 theta A dagger B minus A B dagger A dagger commutator of this plus 1 by factorial 2 then theta A dagger B minus A B dagger commutator of again this commutator. What is this value? Can you tell me what is this value?
It will come as a minus B dagger.
Right? Minus theta B dagger.
Yes.
Plus 1 by factorial 3, this is theta A dagger B minus A B dagger, then this commutator, what will be this?
B dagger anyway doesn't matter. So the B dagger B, that means A dagger will come. Theta square A dagger.
So on. So this is A dagger now plus this is minus theta by factorial 1 B dagger plus this is minus theta square by factorial 2 what will be this? This is A dagger plus so on. Maybe I should write the fourth term also. What will be this? 1 by factorial 4 then theta A dagger B minus A B dagger. What will be this one? This is so this is theta cube B dagger, right? Yeah, because this and this. So then what will be the fourth term? This will be plus theta cube by
Just to do a series expansion.
Yeah, exactly. I think
That's
so.
how they
I mean, he's also doing that also. But
yes.
he used the trick in the middle where that is the also.
So this will be basically A dagger cosine theta and then
Sin theta beta.
minus B dagger sin theta, right?
But one thing I have little bit of so in your unitary operator exponential theta A dagger B minus A B dagger. So theta is real, right?
Theta is real, yes.
And A dagger B is minus A B dagger, that is anti-Hermitian.
Yeah, but this we have chosen in such a way that this as a whole is unitary, right?
Yeah, that's what my concern is.
It has to be, the way we have chosen, this is,
That's why that is unitary, right?
yeah.
Hermitian, then
Real into anti-Hermitian. Oh, Hermitian into some imaginary.
Simple way of putting it is that you have one A dagger B here, so whenever you are writing, one should have this I or minus I, whatever, in terms of x and p's. And there is only one I coming in from each of them because there is only one dagger in each of them. That I goes.
I mean, you need either real anti-Hermitian or imaginary Hermitian.
I think this is fine, right? A dagger cosine theta minus B dagger sine
Fine.
theta, right? Okay.
But
Now,
one physics way of looking at it is just this A dagger B dagger operators. These are
now I
basically
replace it by B dagger because this is same thing, right? Yeah.
With a minus sign, I think.
Which one?
There should be a minus sign.
Where?
Well,
Because A dagger B and A B dagger has a minus sign difference. Right?
No, where minus? Is this not correct with A dagger here?
this is correct.
With A dagger, it's correct.
Oh, for B dagger.
For B dagger, we have.
So that's what I'm doing. So
Oh.
this is replaced by B dagger. Now what should be this? Oh, I should be careful now. This is B. So this should be B dagger. Now here it is. What will be this?
No, he is right. It would be B dagger cos theta minus A dagger sin something.
No,
No?
no. This will be plus then. Plus. Why don't you do this thing? This is.
Yeah, yeah.
B dagger cos theta plus A dagger.
So maybe I'll not do it here. Okay, so I cannot. So this is fine. Now I will not do it here. You can do it minus A B dagger, then B dagger, then exponential of minus theta A dagger B minus A B dagger. So I think it should be.
If we exchange,
Yes.
rename the
Exchange with a positive sign.
relabel A as B and B as A, then
But there must be some positive sign.
Is that correct?
Yeah.
Theta. We can relabel A as B and B as A and theta as minus.
Yeah, of course. That is what I have done.
Yeah.
That is what I have done. Okay, so I think this is correct.
Right.
This is just unitary of like where the unitary.
So you see this. So here is a catch. Catch is that this is your being splitted transformation. So when it acts on A dagger B dagger, so this will be basically what? This will be A dagger cosine theta plus B dagger sine theta. Sorry, I am a bit messy here. So and then this is minus A dagger sine theta plus B dagger cosine theta, right?
either rotate the state by theta or the operators by.
So basically, what we have obtained there is, you can equate with this provided you take the Heisenberg picture form. So what you do is, this is correct, but then you will have to be little bit careful. You should take exponential of minus theta A dagger B minus A B dagger, then A dagger, then exponential of plus theta A dagger B minus A B dagger. And then exponential of minus theta A dagger B minus A B dagger, then B dagger, then exponential of theta A dagger B minus A B dagger, which is expected, right? Okay. So this is in the Heisenberg picture, and that has to be the case. At the level of operators, you should consider Heisenberg picture. Okay, good. So where are we now? We are here. So therefore, see, our life is much simpler now. What is this term? A dagger cosine theta minus B dagger sine theta to the power n, and then this is A dagger sine theta plus B dagger cosine theta to the power m acting on 0 0, right. This is what you get after the action of this unitary corresponding to the beam splitter on n n. So, what is happening here? Basically, you see that
Yeah, we are in the Heisenberg.
yeah, these are in the Heisenberg picture. And now, if you expand it, okay, you will get the this binomial distribution. Okay. So, the total number of photons is n plus m. Now, in which port how many photons will be there, that you will get through this, and which probability, that will get through this binomial distribution. Is that okay? Right. So, if you take a beam splitter and send classical light, if it is a lossless beam splitter, it will act in the same way. I mean, the portion of light which will go towards the transmitted beam, and the portion of light which will go to the reflected beam, the probability will be decided by the reflectivity and transmittivity coefficients of the beam splitter. Okay.
That's kind of, I think, where we can derive this formula in a much more easier way in a classical setting.
Exactly.
You have the electric and magnetic field V and E, and then you have the total energy conservation. So you start off with electric magnetic field in some direction, and then you change this, rotate these fields along another direction. So this is the rotation medium.
Exactly.
And then once you rotate them, you know that that's how you fill these things up.
Exactly.
So you do a semi-classical approach, and then you put these things.
Exactly. Yes. Yes. I mean, there is nothing quantum in it.
There is nothing quantum except the levels, and those levels you can think of it as a quantum.
Exactly. Yes. Okay. So, let us take some interesting examples. I have used formalism of quantum mechanics, that is also true, but just beam splitter action does not introduce anything non-classical. That is what my point is. So, it does not destroy the total number of photons, neither it destroys and neither it adds any extra photon there. Okay.
That is true, but that's only ideal beam splitter.
We are dealing with ideal beam splitter, lossless beam splitter. I will come to that. See, for example, if your input state, joint state, has no non-classicality in it, a lossless beam splitter cannot produce a non-classical output state. Okay. So, the photon number distribution in the input state cannot, I mean, it will decide what will be the photon number distribution, what sort of photon number distribution you will have in the output state.
That is quantum or that is not quantum?
So, in quantum optical sense, when I say quantum means non-classical. Okay. So, you will have photon number distribution which is not present in the classical world. Let me give you some example, then perhaps things will be clear. So, let us take so, I will take these epsilon is equal to phi is equal to 0, which is already I have taken, and I also take theta is equal to pi by 4 for this case, okay, for this example. So, then this is pi by 4. So, this is called 50-50 beam splitter, okay, 50-50 beam splitter. I mean, because the cosine theta and sin theta are basically 1 upon root 2 each. So, this will be a dagger b minus a b dagger. Of course, with phases also one can call, when theta is equal to pi by 4 and there are non-zero phases, still it is called 50-50 beam splitter, but this is the simplest one. So, let us take it on 1 1. So, that means you have this beam splitter. So, here is your gate 1, which is this okay, or you can you can, if you want, you can write in this way also 1. Okay. So, in one beam it is single photon state, another beam it is single photon state, and then I am looking at the output. Okay. So, this is my input state 1 tensor 1. I mean this should be, let me call it at 1 tensor 1. Okay. So, according to this formula, this is 1 upon factorial 1 factorial 1. So, 1 factorial which is essentially 1, and then what will be this? This is A dagger minus B dagger divided by root 2 whole to the power n is equal to 1, right, and then this is A dagger plus B dagger by root 2 whole to the power 1 acting on 0 0. Is it correct?
So when you say A dagger minus B dagger, that means A dagger tensor product identity minus identity tensor.
All those things are there, yeah, all those things are there. So, this is half, now this is A dagger square, right, and then this is plus A dagger B dagger minus B dagger A dagger, because B dagger and A dagger they commute. So, I can also write as minus A dagger B dagger minus B dagger square acting on 0 0, right. So, this will get cancelled. So, what you have is half A dagger square minus B dagger square acting on 0 0, and what is this? 2 comma 0 minus 0 comma means tensor product, okay, 0 comma 2.
So this is that effect.
This is called Hong-Mandel effect. Okay. Some people call it as deep also. So, what does it mean? It means that if I put a photo detector here and a photo detector here, then for this 50-50 beam splitter, so this is 50-50 beam splitter, you can detect either 2 photons here, no photon here, or 2 photons here, no photon here. There is nothing in between. Okay. So, if you think of classical particles, and as I said, this is just binomial distribution of particles through this beam splitter action. So, here you have one particle, here you have one particle. So, what will happen is sometimes you will get 2 particles here, nothing here, 2 particles here, nothing here. Sometimes you will also get 1 particle here, 1 particle here. That may be most probable, yes, but you see here the point is that phenomena is completely absent. So, people generally do what? They put a coincidence count here. This is called coincidence count. So, this counter will click if both the detectors detects 1 photon each simultaneously. Okay. So, this coincidence count will be 0. Yes, yes. Okay. So, this tells you that single photons are of course quantum in nature, they are completely non-classical states. So, which provides you a completely non-classical feature here. This is unheard of in the classical physics. Okay.
So sorry to interrupt.
Yes.
Actually, our connection got broken. So can you briefly just say that experiment part what you are explaining?
Oh, whatever I am explaining. Okay, okay, okay. So, what I am doing? So, this you have seen, right? This formula of this beam splitter when it acts on the n cross m input state, right? This formula. So, now you take a special case when n is equal to m is, so n is equal to m is equal to 1, okay, like this one. So, you have one single photon here and single photon here in 50-50 beam splitter case. So, theta is equal to pi by 4, epsilon is equal to phi is equal to 0. So, then the action of the beam splitter on the input state like this one will be basically according to our formula is this one. So, if you do this algebra, what you will get is this state. So, this means that if I put photo detectors on the two output ports, either this up detector will click with 2 photons here and no photon will be detected here, or this bottom detector will click with 2 photons here and no photons will be detected here. So, this is the state that you will have finally, and which is completely counter intuitive in the classical world, because in classical case if you have a beam splitter, lossless beam splitter, one particle coming here, one particle coming through this side, then there will be cases where one particle gets detected here and simultaneously one particle gets detected here, which is not the case here in the quantum mechanical scenario. So, this is a completely non classical feature that you get to see in Hongo-Mandel effect, and this has been verified several times in experiment, and this is it has plenty of applications. One particular application is to characterize single photon nature of a source. Okay. Single photon nature of a source. Let us say I have a source of light which produces photons. Whether it produces one photon at a time, that can be characterized through this Hongo-Mandel effect. Okay. If instead of one photon it comes with more than one photon, then you will not get to see this kind of effect. Okay. And one important thing is these two should come together at this point, otherwise you will not get to see this effect. Okay. So, those are of course experimental details. So, so this is what you get to see.
This is true for any number of photons, right? Not only one.
So, let us say I take a 2 photon state and 2 photon state here. What is your expectation? Again 50-50 beam splitter. So, does it mean that you will have 4 photons being detected and no photons being detected, or 0 photon is detected and 4 photons being detected? Is that the only option?
There will be 4 2 and 2 4 something.
No, 4 2 cannot be, because you have 2 photons.
Oh, sorry, 2 2 you are taking. Sorry.
Yes.
So if 2 2 is there, then you are applying A dagger square, right?
Yes.
So that means 4 can be possible.
Yeah, that is true. 4 0 or 0 4.
0 4 something like that possible.
Will there be any other option?
There will be 1 3 and 3 1, right? So I mean then you have 1 photon here and 3 photons here. The coincidence not should be.
What about 2 here, 2 here? Yeah. So, what you will see,
A and D, sorry, this is only for 1 and 1.
Yes.
There will be lot of combination to the power A and D.
Yes. So, if you take, so here I am taking n is equal to m is equal to 2 for example. So, then you will see that of course, this option is there, 4 here 0 here or 4 here 0 here. You will also have this option 2 here 2 here. The other option like 1 photon here, 3 photons here, or 3 photons here, 1 photon here will not be there. Yes. So, this is a typical of quantum nature. I mean, it is not as prominent as the Hongo-Mandel, but still you can get to see quantum effect there.
When we send the coherent light,
Yes. So, when you send coherent light, for example, if you take here a coherent state alpha and same coherent state alpha, okay. So, this you can figure out that it will be just a product state. Now, which one will be which, that I will have to calculate. I guess this is the one, root 2 alpha and this is 0, that is it. So, this is a product state again. Okay. I may be wrong, maybe this is root 2 alpha and this is 0, but this is not superposition, okay, just tensor product. So, this means that coherent states being classical like states, you have no correlation here, just here also you have photon number conservation. Coherent state photon number is mod alpha square, this is mod alpha square, this is mod alpha square, this is 2 times mod alpha square, that is fine. Other term will not be there.
Only one single term.
Only one single term. Yes. So, the term will be root 2 alpha tensor product 0, or maybe the other one. Okay.
You were saying something like there is nothing about quantum here. What is that? I forgot.
So, you see coherent states are classical states. Beam splitter does not introduce any non classicality in the sense that no correlation here, okay, because this is a product state
For the coherent state.
yes,
For the 0 0 you got the correlation, right? Entangled state.
not 0 0 1 1, this is 1 and 1
1 1. Right.
yes. So, for 1 1 these are non classical states.
Okay.
So, there under the beam splitter action you get this entangled state.
Oh, so you are saying that if the input state is itself classical, then there is nothing quantum at the output, right?
Exactly.
Okay, if your input state is quantum, then the output will also be
It
a
has to
quantum.
have some reflection in the correlation.
Okay.
One idea that people use is to do lithography essentially. Basically, the idea is that you have one. So if you look at the intensity, then this is like one. So intensity is 1 unit. So you have to tensor the intensity effectively 2 units. But then if you look at each of these outcomes, so this is 2 0, the intensity goes squared. So in each of these two outcomes, the intensity is 4 times. So basically, if you want to burn something through some substrate, I mean, this is what you do like chip etching and things. So this is what people can use. That you have
Yeah.
like 4 times the burning power essentially.
Yes, yes. Okay, so maybe I will stop here. Next time what I will try to do is to give you some physical insight through this indistinguishability of photon paths inside this beam splitter, that why such a phenomena happens. Okay? Okay. Any question?
So it
Any
seems
question?
like in this
Sorry?
example of coherent states that it decided whether to go here or there depending on pi by 4, right? I mean, how
Yes,
does
yes.
it decide where to go? It seems like completely symmetry and A and B the problem, but
Yes, yes.
it
So
goes
this
here
shows,
rather than
if it had it been classical,
yeah.
then it would have been like, just alpha here, alpha here, maybe some phases, something like that, okay?
Yeah, yeah.
Or something like that. But the question is, this is coherent states are, I say, classical like. So it has uncertainties which are my minimum, which is not there in the classical case, and because of that uncertainty, phase space uncertainty, it behaves somewhat differently compared to the classical case. It does not behave exactly same as completely quantum case, but at the same time it does not behave completely classical.
But it seems like if I take minus pi by 4 instead of pi by 4, then I will get 0 tensor root 2 alpha.
Yeah, that is of course there.
It will just split which
Yes,
which
yes.
sort of
I
detector
mean,
it's going to
this, as I said, we'll have to calculate which one is this and which one is this.
Yeah. So that's what I was a bit confused about. Like, how did it decide that I will go there and not there?
No. That you'll have to figure out from here itself.
Yeah. Depending on the sign of
Yes,
theta.
it's from there you'll have to figure out. I mean, I have written it like my memory that this has to be the case.
Sir, if you consider alpha and alpha prime, what will happen then?
Something of alpha plus alpha prime.
Okay, so this for you can figure out that if I take here alpha and beta, okay, if I take it alpha and beta, I don't, again I may be wrong. So you will have alpha plus beta by root 2. This is 50-50 beam splitter,
Okay.
and this should be beta minus alpha by root 2. This may be interchange. We'll have to see.
Oh, so it will remain product, I think, right? Okay.
And not only for 50-50, any beam splitter you take, it will be like this. Okay, good.